Okay, we're back. Let's dwell on this for just a couple more minutes. This was what we had on the board. Let's just see this thing in action for one more example, which is 6. Okay, I'm going to erase these blue things because everything that's on the board now is exactly how far out you would have to go for computing 6. And so let's just do it right now. And so what we need to do is we need to imagine, the goal for this moment is use the infinite generating function above to compute p of 6. And how should we do it? Well, multiply out, no big deal, just multiply an infinite number of infinite polynomials together, and then just look for the coefficient of z to the 6th in that expansion. Well, that sounds like an infinite task, but really it's not, because to find the coefficient of z to the 6th, I don't need to consider arbitrarily large powers of z. In fact, I don't need to consider any power of z, which is larger than 6, because it can't possibly play a role in generating a z to the 6th. And so I basically stop when I get to 6. So 6, 6, 6. I stop here because the next one would be 2 times 4, which is 8, and that's bigger than could possibly be useful. And here I stop at 1 times 5, because the next one would be z to the 2 times 5, which is 10, and that can't possibly be useful either. Okay, so now we're just going to multiply all these things out. So let's go. I'm only going to do the ones, however, I think even if you just delete all these dots, you still have like a very, very large polynomial. 7 terms, 4 terms, 3 terms, 2 terms, 2 terms, 2 terms. So that's 2 times 2 times 2 times 3 times 4 times 7. That's a very, very big number. But you don't even need to do that. You can just kind of like eyeball it a little bit. How am I going to get 6? Well, one way to get 6 is to get this one. And in other words, what I do is I choose 1 out of this polynomial, I choose 1 out of this polynomial, 1 from this polynomial, 1 from this polynomial, 1 from this polynomial, but from this polynomial I choose z to the 1 times 6. So that gives me z to the 1 times 6. And then, technically speaking, for the rest of the infinite polynomial, we just keep choosing 1. So the product of an infinite number of polynomials, so this is one term from this infinite polynomial, is z to the 1 times 6. Okay, going a little bit faster, what's another way to get 6? Well, I could get this, let's get this guy. There's only one way to get this guy, and that is to, once again, do... Oh yeah, so now I'm going to choose z to the 1, so if I multiply those together, though, I get 6, right? And z to the 1 times 1 is 1, so the only way to finish that off would be if I had a 1. So basically I choose z to the 1 times 1, and then I choose 1, 1, 1, z to the 1 times 5, and then 1, and then forever. Okay, and then we just kind of keep on going, right? Z to the 1 times 4 comes up when, there are 2 ways, because the only way to get 6, since that's already 4, is to have z squared, and that can happen either here or here. So one thing to do is I choose z to the 2 times 1, and z to the 1 times 4. Another way to do it is z to the 1 times 2, z to the 1 times 4. And then, what else? Now I want to get that guy. How do I get that guy? Only by having, again, 1, 1, and then z to the 2 times 3. Okay. How else can I multiply all these things out and end up with a power of z to the 6th? Well, I could do this one, so I'm sort of going backwards, I guess, through these, right? This is 1 times 3, so if that happens, then I have to have 3 everywhere else. So I could get I guess it doesn't matter how we do this. 3 ones, or maybe I should just, if I'm going backwards, maybe I should just go backwards. So z to the 1 times 3 times z to the 1, 2, and 1, 1. That'll work. So that one's kind of exciting because it's 3 things. Z to the 2 times 1. Okay. And more. Oh, I could also get that one could also come up. Z to the 3 times 2. So just let's throw that in there also. Plus, what else could we get? Is there another way? Oh, is there another way to get 1 times 3? There is. Sorry, going a little bit out of order here, but just moving on. Z to the 1 times 3 is z to the 1 times, and then I could just do the same thing, right? 1, 2, and 2 ones. I guess those are the 3 possibilities, or 3 ones. This kind of sucks. Yeah. Z to the 1 times 3 times. Oh yeah, that's the only other way to get 3 besides 1, 2, and 2 ones is just 3 ones. So that factor would fall out from the mindless multiplication of that one, then I choose a 1, then I choose that one, and then 1 subsequently. Okay, we're almost done. What's another possibility? Another possibility is 2 2s and 2 1s. So that would be here. So I guess we're sort of moving backwards now. Z to the 2 times 2. And if I had z to the 2 times 2, then that would be multiplied by z to the, well, I could do it either with 2 1s. I guess I can only do it with 2 1s. And then maybe there's like 1 more or 2 more. I could do, moving on to here, z to the 1 times 2. Well, now that leaves 4 left over, and the only way to do that that hasn't already been taken care of is z to the 4 times 1. And finally, then we have z to the 6 times 1. Okay, let's count all these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And so 11 z to the 6th, what I have just computed in a sort of a little bit cheating because I had to think a lot about what I was doing as I was doing it. But if you did it mindlessly, it would just take longer. What I've computed is that in this infinite polynomial, it must be the case that the coefficient of the z to the 6th term is 11. And that means that, if you believe this, that means that p of 6 is 11. Let's check it by just doing them all. I'll put down my paper and I'll just do this using my wits. You can do 6. You can do 6 as 5 plus 1. You can do it as 4 plus 2. You can do it as 4 plus 1 plus 1. You can divide those puppies up as 3 plus 3, or as 3 plus 2 plus 1, or as, make sure I'm not missing any, 5, 1, 4, 2, 4, 1, 1, 3, 3, 3, 2, 1, 3 plus 1 plus 1 plus 1. Then there's like 2 plus 2 plus 2. Then there's like 2 plus 2 plus 1 plus 1. Then there's like 2 plus 1 plus 1 plus 1 plus 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Look at me. And the 11th one is where you just have 6. Okay. So by just using my brain and being careful, I have computed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, but I don't think I messed up. I have computed that there are in fact 11 ways. I've listed the 11 partitions, and therefore p of 6 is indeed 11. Okay, this is the one and only time this semester that we're going to talk about generating functions, so maybe that was worth it, maybe not. Okay, and we got a nice introduction to the actual thing that we're trying to count here, which are these partitions. Okay, well, good. Moving right on, the sort of stronger combinatorial object that we care about even a little bit more than partition numbers are partition numbers with a certain specified number of addends. Okay, so I hereby introduce you to the slightly related but actually different thing called PNK. And okay, I didn't write this down, so maybe I should lean on Gossett for the precise definition. PNK is the number of partitions of n that contain exactly k summands. Yeah, so that's not so hard. That's exactly what I said. Is the number of partitions of n which contain exactly k summands. Oh man. Okay, I feel like I had some sort of example of this, but I don't know. Let's do like P73 or something like that. Okay, what's P73? Well, we're considering all the partitions of 7, but instead of considering all the partitions of 7, we're considering the partitions of 7 for which there are 3 numbers. In other words, if we're dividing up some 7 puppies into piles, we're counting now not the number of ways to divide the 7 puppies up into piles, but the number of ways to divide the 7 puppies up into 3 piles. Okay, and this is assuming the puppies all look exactly the same. Okay, well, just off the top of our heads, using our wits and stuff, what is the way to do this? 5 plus 1 plus 1 seems to be an option. And another option is 4 plus 2 plus 1. And another option is 3 plus 2 plus 2. And another option is what's another option? I guess, could that be it? That would surprise me, but it wouldn't surprise me that much that was it. 1, 2, 3, 4, 5? Am I missing one? It's very embarrassing if I am. I feel like that's it. This is the most unfair way to do it. This is the most fair way to do it. Have I missed one in the middle? No. What are all the ones with 4? Then it has to be 2 and 1. That's the only one with 3. Oh, of course. 3 plus 3 plus 1. Okay. Phew. That was almost really embarrassing. 3, 3, 1. Because you can give that puppy to that one. In which case it's 3, 3, 1, or you can give that puppy to that one, in which case it's 3, 3, 2. Okay, but now I think that's probably the right answer. Okay, and so, since, I hope that's right, since these are the 4 ways listed out by exhaustive search by a fallible human, that means that P73 is in fact 4. Okay. Or I'll just say equals 4. Okay, good. I think you now understand what that is. And now I would like to compute these. Okay, well, it turns out, and this is a sort of a shocking moment for all of you, that way back, if you go back 2 months ago to when we first started doing counting problems, I tried to make a big deal about, I think I did make a big deal, successfully, about trying to convince you that, like, n choose k, for example, was like a combinatorial object. Whereas in high school, typically people give as the definition of n choose k, they give an algebraic definition. They do some, n factorial, oh, what the hell am I doing? Over k factorial n minus k factorial. They give this as the definition of n choose k, whereas I think that, and then they argue that that this correctly counts a certain combinatorial things. Instead, I think the better way to do it is to define n choose k as a combinatorial object. So to give it the meaning, give the symbol the meaning, the number of ways of choosing k objects from a set of n objects, and then to sort of discover the formula. Okay, well now we see why that's maybe a good way of thinking, because here we have a combinatorial problem that we sort of want solved, which is the number of ways of doing this. This would be if you have 7 puppies and you get the call that 3 orphans are coming later this afternoon, and so you need to start dividing those puppies up into orphan piles, or puppy piles, but 4 orphans. And the answer is there's 4 ways to do this. Okay, so there are all kinds of different, maybe more realistic cases where you might want to do something like this. And so I just want to stress that we have defined this symbol as the solution to a combinatorial problem, and now we go sort of hunting for the formula. And sadly, there's just no formula. Or to be more precise, there is no simple closed form expression that will algorithmically compute this in terms of more well-known and simple algebraic objects, unlike the simple formula for n choose k. And so, if that's the case, if there's, as a kid might say, no formula, then how are we ever going to compute these things? And the answer is recursively. Yeah. So here is the theorem. Maybe I can't remember how I'm supposed to teach this, but I do know what I'm talking about. This is known as a recurrence relation. Or it's sort of a method to recursively compute these things. Okay, and so here's the theorem. It says that Pnk is the following. It's Pn minus 1, k minus 1, plus Pn minus k. Okay, with some boundary conditions established, and that is, they're all kind of like boring. If k is greater than n, well, okay, that's just stupid, because you have only n puppies, so you can't divide those puppies up into more piles than there are puppies. So if k is greater than n, then Pnk is 0. So that's like obvious fact number 1. Obvious fact number 2 is that Pn0 is 0. That just says that you can't divide n up into 0 piles. So these are the sort of base cases of the recursive computation that we're going to do. And also that Pnn is 1. In other words, if you are going to, that there's only one way to split n up into n piles. I'm not even sure I need that one. Okay, so let's go. What is this? Why is this true? Why does this sort of make sense? Okay, first let's explore a particular example. So take P9,4. Okay, what is P9,4? It's the number of ways of dividing up 9 puppies into 4 piles. And it might be worth it to just write those out right now using our wits. And I happen to know that there are 6 of these, so this time I won't screw up. But I don't have them listed here, so okay, let's just try this. If it's going to be 1, so the 3, 6, so 6 plus 1 plus 1 plus 1 is one way of dividing up 9 into 4 piles. Then there's 5 plus 2 plus 1 plus 1. Then, if this pile loses a puppy, then that would be 4 plus 3 plus 1 plus 1, or alternatively 4 plus 2 plus 2 plus 1. And now, those are the only ones where the biggest number is 4, I believe. And then you could do I believe that? Yeah. And then you could do 3 plus 3 plus 2 plus 1, or 3 plus 2 plus 2 plus 2. And there's no more fair way of doing it, so that is good. And we got the 6, so that seems right. Okay, and the claim would be, so suppose you find yourself wanting P94. Well, you got two options. You can do what we just did, which is just use our wits and hope for the best and just do it out by brute force. Or you can compute P94 using this recursive rule, which we've yet to understand. First, let's just like execute it. What does it say? It says that this should be P83 plus P54. Okay, well, what is P83? Okay, P83 is the number of ways of dividing 8 up into 3 numbers. So now that would be 6 plus 1 plus 1, 5 plus 2 plus 1, 4 plus 3 plus 1, 4 plus 2 plus 2, and 3 plus 3 plus 2. I believe that there are 5 of those. And I did that kind of fast because I sort of know what I'm doing now. 6 and 8. Have I done something wrong? 4, 3, 3, 2? No. 4, 3, 1, 4, 2, 2. Yeah. Good. And how about 5, 4? Well, here, if I want to divide 5 up into 4 piles, then there's only one way to do that. It's going to be like this. Okay. So this appears, if you trust these, you can double check them, use your intuition. But it appears that this at least works, at least for this case. Okay, what is going on here? How can we understand this? Well, it is impossible to avoid noticing that there is some sort of correspondence here between dividing up 9 into 4 piles and 8 into 3 piles. And in fact, and I will draw with an arrow here to stress this correspondence, that if you give me 1 fewer puppy, then that means that, or maybe I should say, maybe the way to think about it is, if you already have P83, and now you give me 1 extra puppy, which would be the way of constructing P94, would be you suddenly give me, yeah, this is the way to think about it, right? Suppose you have 8 puppies, and you want to divide them into 3 piles. And now you've suddenly been given a new puppy. And you've also been allowed to, so one thing you could do is just make a 4th pile. And so for every way there is to, divide 8 puppies up into 3 piles, there is a corresponding way of dividing 9 puppies up into 4 piles in which one of the piles is a 1. Okay, and now what's to be made of this? Well, you notice that the last way of dividing 9 up into 4 piles doesn't have any puppy alone in a pile. And that's because maybe you think it's cruel to there were 101 of these puppies after all. It would be sad to send one of them home alone with an orphan. So maybe you want to make a rule that every puppy pile's got to have at least 2 puppies in it. Well, if every puppy pile has to have at least 2 puppies in it, then we're in this last case here. And now we see that if you have 9 puppies, and you are insisting that every pile have at least 2 puppies, then you might as well, in making your 4 piles, put 1 puppy in every pile just automatically. Having put 1 puppy in every pile automatically, now we just have the P54 problem on our hands. In other words, to complete the 4 piles of 9 puppies, one may simply put 1 puppy into each pile, then just distribute the remaining 5 puppies to the remaining 4 piles in however way there is to do that. And in this case, that's exactly what P54 is. P54 is the number of ways of dividing 5 puppies up into 4 piles. And so the 2, 1, 1, 1 bears a direct link to this sixth way of partitioning 9 into 4 piles. Namely, it's the one you get by adding 1 to each of these numbers. Okay. Good. I think this is now just completely clear, and now we are prepared, I think, with the intuition to prove the theorem in general. And how do we prove this theorem in general? So I'll erase these question marks. Well, you do a combinatorial proof. I am feeling kind of lazy, so I don't feel like, well, I don't want to write all this out. Maybe I should, though. The full combinatorial proof of this recursive rule would now, well, you would do a combinatorial proof. You would say, claim both sides count, and notice that you only have access this time to a combinatorial proof. You can't do this quote-unquote algebraically, whatever that means, which some of you were perhaps tempted to do in the previous unit, by just sticking all kinds of disgusting giant algebra into your formulas and just cranking them out and showing them the same. Here there is no algebra because fundamentally this is a combinatorial object, so only a combinatorial proof is possible here of this recursive rule. Okay, claim both sides count the number of ways to, and I'm just going to write arrow because it's the number of ways to partition, well, no, maybe I should. Both sides count the number of ways to divide, or to disperse. No, not disperse. I'm just going to say make. Both sides count the number of ways to make 4 piles of puppies. Out of 9 indistinguishable puppies. Indistinguishable puppies. Alright, so I don't have space. I'm going to claim that I don't have enough space on my whiteboard to do this properly because I'm feeling kind of lazy. But if we were doing a full quality combinatorial proof now here, we would say, suppose we have n puppies. And we are going to divide those n puppies up into k piles in preparation for k orphans coming later that afternoon. Claim both sides count the number of ways to make 4 piles of puppies out of 9 indistinguishable puppies. And these piles are obviously non-empty and the puppies are all indistinguishable, so I think that's good. Well, the left-hand side is just true by definition. That is precisely what PNK is. It's the number of ways to divide n indistinguishable objects up into k non-empty piles. So now on the right-hand side is where all the work is. Why does the right-hand side also count that? Well, notice, once again, that there's a big plus here. This big plus is screaming the addition principle is happening. And so I hesitate to use the word partition because partitions are under discussion, so I won't. I will say, we proceed by cases. On whether, this is what we would have previously called a partition, on whether or not any puppies are to be alone in piles. Okay, and now if none, if alone is okay, no, not if alone is okay. If whether or not any puppies are alone, not are to be alone, are alone in piles. If a puppy is alone, then, and I'm going to finish this out by talking it, and if no puppy is alone, then I'm going to finish it out by talking about it. Okay, so what I'm doing right now is this gets hard, right? I am counting on the left-hand side the number of partitions of n into k piles, n puppies into k piles. And now, considering all of the possible partitions, in this case there were 6 partitions, but in general there might be very, very many partitions. I am now taking all those partitions and I'm splitting them up into 2 subsets. The first set of partitions to consider are partitions in which at least one puppy is alone in that partition, which is just another way of saying that at least one number in the partition is a 1. That's what it means for there to be a puppy that's alone. At least one of the piles has only one puppy in it. Well, if at least one of the piles has one puppy in it, then what we could do is just ignore that lone puppy and then take a look at the other 3 piles. If you are sure that your partition is going to contain a lone puppy, then if there's always one lone puppy at least, then, well, now just look at the rest of the piles, the k, because initially there are k piles, so now take the k minus 1 piles, and ultimately this problem reduces to distributing n minus 1 puppies to the k minus 1 remaining piles. Okay, so in other words, for every partition in which there is a lone puppy, there is a matching partition, which is what I tried to do with the purple arrows, of one fewer puppy into one fewer pile. Okay, now if on the other hand no puppy is alone, well, that means that your k piles do not contain, all have size 2 or greater. Well, if all your piles have size 2 or greater, then simply remove one puppy from every pile. And, or rather, as I said it before, place one puppy into every pile automatically, and now the number of ways to complete that partition in which no puppy is alone is just to distribute the n minus k remaining puppies, because you had n puppies and you put one puppy in each of the k piles, and so n minus k puppies remain, and then there are pn minus k comma k ways to distribute those remaining n minus k puppies into the k piles, by definition. And this is I forgot what I was going to say. This is the number of ways to do it, and so if no puppy is alone, and so since every partition either contains a lone puppy or doesn't, then we have counted every possible partition. Okay, that I think is very clear, and what it means is that we now have a recursive rule. Okay, why is this recursive rule great? Because this recursive